Okay, let's meet to each other. Actually, on this masterclass is working several people, not only me, and also two of them are here. Two girls, Alexandra and Alessia, and they will help you to calculate on your task when we come to them. And here, people mostly from NOvA experiment. And we will work on the with events from this NOvA and calculate energy of the neutrino events, and then try to make the calculation for oscillation parameter. Also, I would like to introduce our colleague Linda Cremonesi from the Queen Mary University of London, who is actually the initiator of this masterclass for students in London. And then we adopted for another format for you. On the background, you saw and see now the remote operation center for NOvA experiment, located in Dubna. And it works to monitor working of the far and near detector of the experiment, make some, I don't know, training or control the working of the beam and detectors, and monitor that everything is okay. So, what you hear about neutrino, at least it's fundamental particle, very cool, and sometime can produce you the prize. Like I think this next Nobel Prize will be for thing related to neutrino, and who explain why we have an asymmetry in our universe and between the matter and antimatter. But the last prize for Nobel Prize for neutrino study was in 2015 for two collaboration actually, and here the leader of this collaboration, Super Kamiakande and SNO. And what they make, what they measure and discovery of the neutrino oscillation, and that, as I say in this Nobel Prize, which show that neutrino have mass. So first, Super Kamiakande. Why? So why it's so important and why it's for the Nobel Prize? They actually show that we have a flux of neutrino without oscillation and neutrino with oscillation. Because before the people see the access of the neutrino, but they not be sure about the flux of the neutrino. So, and they measure unoscillated spectra from top and oscillated spectra from bottom, and you see the difference between the prediction and the actually measured. Another collaboration, SNO in Canada, make a little bit different stuff, but also with the same concept. They measure several interaction of the neutrino, and one of them shown that for neutral current, and neutrino have a flux predicted with the sun, neutrino from the sun, and then another channel with the oscillation. And here the list of Nobel Prizes, it's actually 4, connected to neutrino, and I will not explain everything, and if you will be interested, you will see it in the slides. And here a short history of the neutrino and different study and measurement and prediction from almost 100 years ago to 2012, and there's some more results appear in the last 10 years. So what actually in this neutrino feature, so we have particles, quarks and leptons, what is neutrino. Then we have a boson, what interact between these quarks. And if you see the interaction between the quark through the CKM matrix, so it's actually show you the interaction between initial state and the final state. And in neutrino, we have so quite similar concept, but we have in the source and in the detector, so different feature, and we detect one type of, produce one type of neutrino and detect another one. So it's through the so-called, that neutrino have mass eigenstate, then mixing matrix, and then the flavor neutrino, what we actually detect. So, and this idea was suggested by Bruno Pontecorvo, and he was like fun and make some mysterious things. So produced as the one or us, then make a mystery. So with this neutrino and appeared another neutrino. So it's like the matrices in with some parameter what was already measured, and the feature called by actually type of the detecting of this neutrino. And today we will talk about so-called long baseline neutrino, what is connection to neutrino from accelerators. So the first generation was about 12 years ago. So one experiment K2K in Japan, another minus in the US in the Fermilab. And there are some parameters what they measure the muon neutrino in the source and try to measure disappearance of this muon neutrino in the detector. So this is Super Kamiokande and pretty similar stuff in the US, the beam in Fermilab, and then detector in Sudan. So they measure so-called disappearance channels. So this is, you see, predicted flux, unoscillated for buff experiment, and then measure flux, what is disappearing. And for this, we can calculate quite simplified formula from the matrices you see before, and so-called the probability nu mu to nu mu. So it means that we have a muon neutrino in the beam, and then some excess and less muon neutrino in the detector. So there's some parameters, and they actually not measure the mixing angles and delta M precisely, but catch a hint that neutrino are disappeared. So the current generation, also in Japan and US, T2K experiment and NOvA, the same concept, but they add also appearance channel and detect also electron neutrinos. So what actually it's looking for, again, for example, on NOvA, the Fermilab beam, then it's modified and go to place pretty close to the Canada board in the Ash River, and then this colored band is the changing from muon neutrino to another neutrinos. So mostly actually nu tau, but the parameters what we are looking for more connected to electron neutrinos. So it's some features, and first this is a problem of hierarchy, mass hierarchy. So it means what is the lightest neutrino, electron or not. For example, you can see M1, M2, M3, or M3, M1, M2, because we know the difference between this composition and this, but not the limited one. Another feature, how we can measure it through the so-called zero neutrino double beta decay, and this is also a measure for neutrino Majorana or not, and also for this mass ordering. And together they could make the more information about the neutrino properties. So then another problem, it's a difference in the so-called delta CP. So this is violation CP phase. And we should look the oscillation between neutrino and antineutrino with appearance channel. And this is go to all of this stuff, including the problem of asymmetry for the matter and antimatter, and also measure these parameters more precisely. Okay, and through the disappearance channel, it's connected to composition for third neutrino, and this is quite a little bit of composition of nu e, and mostly the half of nu mu and nu tau. And this is connect to theta 2-3 parameter, and if they are equal, nu mu and nu tau, we have a theta so-called maximal value, 45 degree. But if we have some shift here, we can have more 45 or less 45, and it's connect to nu tau, more composition for nu tau or nu mu. And this is measured as in the previous Minos experiment through the disappearance channel, and here the curvature to disappearance for nu mu as the parameter of neutrino energy, and through measurement this gap for value of the energy and the disappearance stuff, we can measure theta 2-3 and delta m square 3-2. And here it's last task in the masterclass. Okay, and through this channel we can measure actually only up to 45, up to maximal angle, and to make the difference between if it's more than 45, you need to also measure the appearance channel through. So it's measured through this plot on NOvA. So here it's probability for neutrino, here a probability for antineutrino, and through the degeneracy of these parameters, we can measure mass hierarchy, this theta 2-3 stuff, and also delta CP. This is a mixture. So this is how the beam produced in the Fermilab. So we have a proton beam, then target, composition of magnet horn, and decay channel, and we have finally the neutrino, mostly of muon. Okay. This is how NOvA and T2K normally works. This the so-called proton on target, or number of neutrino we get on the detectors. Here the flux, and for NOvA it's mostly 2 GeV. It's a special feature that so-called off-axis stuff, and through the this decay channel for pion and kaon, we have mostly the narrow peak close to 2 GeV. In different experiment, it's a different concept. It could be, for example, on axis, and what actually was used for K2K and Minos, and it's pretty close to this one. To measure oscillation, we have to have 2 detectors. One to measure the unoscillated spectra close to the beam, and another one, so-called FA detector, what we actually measure the oscillation. And you see that for neutrino physics we have a very huge detectors, and the FA detector, it's 15 by 15 meters, and you see the person staying here, it's in comparison with this one. What's in the NOvA? NOvA consists, it's quite boring actually. It's the PVC cells filled with liquid scintillator, and through the rescattering and having wavelength shift fiber and the photodetector, we have a signal in small cells. And events usually look like this. And you see on the first task and the first list the type of events what we actually detect. So first one is so-called nu mu CC, nu mu charge current, what is actually the catch muon neutrino through appearance of muon and the hadron. One hadron like this proton or more. And this is normal topology for nu mu CC event in the event display. So another one, it's also charge current, but for electron neutrino. And here we catch electron neutrino. We have a shower more fuzzy than muon track. So this is straight line, almost straight line. But this is a shower and also hadron activities. So also we have some backgrounds. And for example, for neutral current. And here it could be anything and in the detector, but this long track, it's almost invisible. This is hadron activity here, and sometime it's produced pi zero, what actually decay into 2 photons. And signal from photon and electron pretty similar, but here it's more fuzzy. It's more scattered in comparison to electron neutrinos. And to detect all of this event, we have used artificial intelligence and machine learning technique. So so-called convolutional visual network. And it's recognized a feature, what I just tell you. So, for example, track length or showers or another feature like the big shower for the hadrons and so on. And today you will work as this not artificial man recognized visual network, and try to do the same thing in the first task. So this actually you have printed, and then try to follow all of this and use your list to recognize next 10 events. Okay, so just to remind you, electron neutrino, what is this? Who can recognize it? This is neutral current. And what is this? Charge current. And which one? Electron or muon? Muon. Okay. So and then you just write for each event number, and then what you guess, which event is on the slide. Okay. Are you ready? Hope so. The first event, what do you think? What is this? Just write on your list. So let me know if you're done. Okay, so let's go to second event. So you put number 2 and guess what is this? Yeah, so Sasha said that actually I didn't say you that we have a 3D detector, but we have 2 projection. One of them is XZ, another YZ. So and the top one is XZ projection, another one is YZ. And if we make it together, we have a 3D image. Okay. If you done, we can go to the third event. So take a guess. Oh, no, sorry, it's the previous one. Event number 3. So now you can think, compare with examples, and then take a guess, what is this? So new ECC, new MUCC, or NC, neutral current. So let's go to next event?
Yes.
Okay, good. Now it will be going faster, I guess. So the event number 4. So let's go to next one, event number 5. Much smaller than previous ones. So are you ready for next one? Yes, okay.
How many events?
10. It will be 10 events, yeah. Event number 6. Actually, this event have a lot of energy deposition in the detector. So remember the features: long track, fuzzy shower, or hadron shower, what is actually more fuzzy. So next one, event number 7. Okay, 3, 2, 1, event number 9. 8. So I guess you're ready for next event, number 9. And the last one, event number 10. Okay, and if you are done, if we recognize all of the event as they detect in the experiment, and actually in the near detector, we detect millions of such kind of events, and in far detector, hundreds. And then after that, what we should do with this event? What do you think? Reconstruct what? The energy, right. So and now the next task, we will reconstruct energy, but particularly for muon events. Then actually procedure not so simple as explained here, but we will try measure the energy with the simple approximation. So first of all, you see a long track. What is muon? And to measure energy of this muon, you have a measurement things. So I forget the word. So, but anyway, so you should measure a ruler. You should measure the length of the muon in the longest projection. So you have two projections, xz and yz. So choose the longest one, measure the length of this track, then so you have a scale on the projection. Make the scaling by measuring the ratio between your ruler and z-axis. Calculate with this formula 200 MeV plus k, this scale, multiply by 2, what is actually ionization loss of the muon, and the length in centimeters for your muons. So if you catch it, another part of the energy will be hadron energy. What is actually using as a calorimeter energy. So, and the average value for all of events in the simplest approximation could be number of hits in buff projection. So just exclude muon track, then calculate number of all hits in buff projection, including the double ones. So you should calculate all of the hits. Let me show on, for example, on this. So if you see like, so maybe in the previous slide, if you see the hits like this, so this is one hit. This one is two hits, calculated as 2. And here it could be 4 or 5. And then you should calculate all hits in these hadron activities. And also here, excluding, for example, like just take a guess that, for example, it's a muon track. It could be not the muon track actually, but so remove this one, the longest one, and then calculate all the hits and multiply by 40, what is approximately average value for hadron activity. And to find total value, what you should do, just sum energy of the muon and the hadron activity. So, and of course, in the real experiment, we have more advanced algorithm to measure this energy. So write code and use artificial intelligence and so on, make some calibration and all of this stuff. And from this 5 events, you see the actual value for this energy. So what is, it's so-called official estimator. So for first event, for second, for third, for fourth, and 5. And this band is the error, experimental error on these particular events. And here the dots, it's from the previous masterclass how people measure this energy. And you see that the error for people with this more simple formula, of course, more less less definite. So the bigger errors on these events. Okay, and then the third task, it's more challenging, and it will be your homework. So, and it's measurement for oscillation parameter through this disappearance channel. And again, so we guess the simple formula to this disappearance probability, what is 1 minus sinus square 2 theta 2 3 sinus square this component including delta m square 3 2 and this value for oscillation baseline L over E. So what you need to do in this task? So actually, as from the first list, you see 3 pictures. So one of them is the measured spectra in FA detector. Then the second one, the also measured spectra in the FA detector, but the red one is the for unoscillated hypothesis. So, and to measure this parameter, we need to study ratio of these two spectra, what actually the third picture. And this third picture, so with much bigger scale, you can find on the fourth list. So then, what you will do, and it's actually explained in the task. So first, find the position of the minimum in neutrino energy spectrum. So in the ratio of the spectrum FA detector to near detector or unoscillated spectra to oscillated spectra. Then, using the obtained minimum value of the energy, so this x-axis, at the baseline distance, what actually for NOvA it's 810 kilometers, calculate delta m square 32 in electron volts. So if you will use length in kilometers, energy in GV, and this stuff here, guessing that this is maximum of disappearance. So you will calculate through this one, this delta m square 32. Did you catch it? So you need to put this value to unit, to 1. Once you done it, then, wow, it's not correct actually. So you need to make the guessing maximum probability to oscillation to calculate this one. And I think in the list it's the right phrase. And then you will find the maximum value of theta 32. And in this task, you will find delta m square and mixing angle theta 2 3. So, but just a few minutes to explain what actually we'll usually do after that. So, and here as the looking for the unoscillated hypothesis and what we measure, and here you can, oops. Sorry. So sorry, it's not K0 because it was animation in the like PowerPoint presentation, but this is PDF file. And but changing the parameters of this delta m square or mixing angle. So this curvature is modifying and in some value make a best value for prediction. And so what actually done for here, it's you see the best prediction here and this data measurement for these parameters. And then for final results, it's using not only the new mu disappearance channels, as I said, also new E appearance. And here, what we detect for new E events, what you actually also recognized in the first task. And here, it's of course events less than for new mu, but anyway, so we have, for example, for results 2024, 181 new E event and 332 anti-new E event with some bins and have some hypotheses, also best fits. And then we have some point in this plot I shown before. So this is probability and number of events for new E channel for neutrino, and this for anti-neutrino have some points. And actually from this stuff we cannot recognize which value for delta CP, the mass ordering and theta to free octant precisely, because we have a point just in the middle. And that's why after that we are joining with T2K experiment and make a joint fit, and it may make more statistical, statistically important result for the final stuff. And here, like many stuff working like, with different hypotheses, for example, in Bayesian or frequentist approaches, and make the results. So make some fits and the plots more precisely than just this simple calculation from formulas. And as a final reminder, what is NOvA experiment? So it's oscillation experiment and the second generation. But to make more precise result, we need more. So another detector, another concept. Detector design, just to remind you that we have two detectors, one near, one another far. So we predict and measure unoscillated spectra, extrapolated to the far detector, and then measure the oscillation stuff. We have a beamline configuration trying to make the more monochromatic beam to make, again, more precise results. So distance for far detector is 810, and the program actually much broader than only oscillation stuff, but also some physics beyond oscillation things. And the next generation, again, for accelerated neutrino experiments will be in Japan. It will be called Hyper K, actually the same distance but much larger detector. And again in US in Fermilab, so Dune experiment, and also with more distance, more intensive beam, and more energetic beam. Okay, I think this is my last remark, and make the last task and bring it tomorrow. If you have a question, please ask, and If not, I hope you enjoyed it.